Share my screen. Oops, you see this is much more interesting. The lecture today, and you can see my screen now, is about the future of very large-scale integration. I'm from the Department of Physical Electronics, EE at Tel Aviv University. I'm also a visiting professor in Waseda Daigaku in Tokyo, in Torino, and Thapar Institute of Engineering in India. So without further introductions, this lecture is about the future of VLSI, and it's always good to remember the very famous saying of Niels Bohr, the famous scientist, that prediction is very difficult, especially if it's about the future. So everything I'm going to tell you today, you have to be critical and you have to understand that things are changing and the progress in VLSI is extremely rapid. So we can meet again next year or the next year and keep predicting. Why we are doing this? Because there is a race for better computing systems. If you think about it, there are a lot of things. We have Moore's law, and Moore's law, I'm going to review it shortly. It says that every 2 years we get better system, better performance, cheaper, faster. But we have three walls. We have the Moore's law, the shrinking law, the how low we can go, how small we can make. We have the memory wall, how much memory we can tolerate and handle, and also the heat wall, which is how if you make very dense devices, you spend a lot of energy per unit area, and heat is being generated. And we have the CMOS driving CPU and GPU, and we have all this better memory storage and bio-inspired computing and in-memory computing, all this. And we want to do cognitive and big data and Internet of Things. And the future of computing depends on our capability to drive this vehicle faster and safer and make it better. So in computing systems, and I took this from a few recent lectures, we can talk about CPUs where we have single core, double core and cache memory and DRAM, or GPUs when we have a lot of cores and a cache memory and again DRAM, or maybe multi-core processing units where we have device level grains in memory computing, all these buzzwords. And I'm going to show you later that the progress today, if you talk about VLSI, and in VLSI we talk about scaling, making devices smaller and smaller. I'm going to show you a new paradigm, a new paradigm which states that it's not enough just to make things smaller. It's not only technology, it's not only design, we have to combine them together. So this is the moral of the story of today, that we have a lot of problems. For example, let's jump on and say, we can think about new systems like neural network, and we have learning and maybe intelligence, billions of people invested a lot. Or quantum computing or superconducting electronics, quantum speed up, a lot of money was spent. Neuromorphic computing, implementation of neural networks. The idea is that we have people, okay, the performance limit or other capability, we can overcome thermodynamic issues, a lot of it being invested. A lot of novel devices. I'm not going to show you all the novel devices, just the list of devices can take few screens. The performance limited thermodynamics, analog computing, thermodynamics, 3D plus architecture, or continuation of Moore's law, which means we can overcome or go around scaling by doing 3D integration, which is actually, if you see, trillions have been spent, and this seems to me one of the most promising directions, and I will show you some very promising structures. And reversible computing, arbitrary low energy operation, still undergoing. So you see a lot of directions are possible. And if you talk about computer systems, one of the very interesting issues is that if you look at the size of the systems, If you think about it, initially it was huge, the size in millimeter cube. And this was presented in 2019 by Professor Sakai and Professor Oba from Todai from Tokyo University in a conference in IEEE, sorry, in the journal. And you can see that in 1946, systems were huge. 2018, the systems, we talk about PCs, iPhones, Apple Watch, or maybe other products. If you are talking about very small, in the future, maybe we talk about wearables and implants. We can talk about very, very small systems with very, very low power. So one of the advantage of making very small systems, we can actually make them very low power if we make them very, very small. So, but if you talk about the big systems today, they are in the range of fusion 9 by 9 millimeter, or if you talk about memory, sensors, CPUs, they are still in the range of 50 millimeter cube. And this is like a typical dimension. So you are dealing if you're dealing about the progress in VLSI, on one hand, we talk about very small system, very low power. On one hand, how to make our current systems better, faster, and cheaper. So let's spare 5 minutes about the fundamental limits of computing. If you talk about a basic computing unit, you have an input 0 to 1 and output 0 to 1. So we can think that we have the initial state and final state. We have some energy barrier in between, some distance between the states. And we can apply some very classical physics. And the basic assumption that our computing system in VLSI, we allow the basic unit as 2 states, and the states are distinguishable, which means we don't have error. So this is the basic assumption in computing. So having said this, so we say the classical limits, we say the energy needed to change a bit at room temperature is the Shannon von Neumann-Landauer expression. And the energy per bit, the minimum possible energy per bit is kT lambda 2, which is about 17. If we take in potential, is 17 millivolt. If we take in energy unit, it will be 17 milli electron volt. So this is the minimum separation you can need. So if you want to build a computing machine, you need to have 2 states and you need to separate them with at least 17 millivolt at room temperature. And you have the quantum limit. And if you take the Heisenberg uncertainty principle, if they take the energy from the bit of 17 millivolt, then delta T must be larger than 0.04 picoseconds. And now we can even go further and say, okay, if we take the Heisenberg uncertainty principle, if this is the delta X times delta momentum larger than the Heisenberg constant, then we can say delta X, the distance of our device should be larger than this dimension. And if you put the numbers, and if you put 17 millielectron volts, you get 1.5 nanometer, which means once we start to reach the 1.5 nanometer range, we are going to have quantum issues. But this is because we define the minimum energy for computing based on thermodynamics. And you can even go further. You say, if I reach the limit, the power is n, the number of the devices, energy per time, this is the power, and the number of components is 1 over the minimum dimension square, which is a few tera devices per centimeter square. And then we get a ridiculous number, which is 3.7 megawatt per centimeter square. And listen, the temperature in the surface of the sun is only 6,000. So it means something is wrong with this limit. And we are not going to reach this limit. Temperature is going to be much more serious limit than all these quantum futuristic devices. Temperature, temperature, temperature. Heat dissipation is a big factor. So if we look at the quantum limit, and we say, oh, let's, instead of thermodynamic limit, let's go for the quantum limit. We have 2 states. And we have, this is the probability of the electron to jump over the barrier. but we also have the probability to tunnel through the barriers. And this, we take the WKB approximation. When we see the probability of tunneling through the barrier is given by this expression, which is, if you see, it depends on the distance between the two wells. You can look at it like the source and the drain of your transistor. And we say if you have two distinguished states, you can assume that the probability of error is this probability plus this probability minus the multiplication, because we take the probability for error. And let's say we allow 50% error, which is like really bad. And if you do this number, you can calculate the power and frequency, and you got ridiculous numbers. You got ridiculous number because you neglect the temperature limits. Cooling is important because if you're generating heat, your device is in temperature T and your ambient or your heat sink's temperature T. You have the heat flow, which is H, which H is the heat transfer coefficient, which is determined by the material constant like specific heat, viscosity, thermal conductivity, heat capacity, etc. So when the temperature of the device is smaller than the ambient or the sink, it appears from the first section that E bit gets better. And if you look at the Carnot theorem, assuming like a fully reversible system, you can calculate the energy per bit. And if we put it into this nice graph that was presented by Tiwari from Cornell in 2017, we can look at energy per operation versus feature size. And if the feature size will be 100 nanometers, and this is the limit of KT ln 2, which is the Landauer limit, we can get 10 to the 21 joule per operation. However, if you look at current CMOS devices are here, are 10 to the minus 16, 10 to the minus 17, 10 to the minus 18. So you can see here that logic operation today are orders of magnitude than the physical limit, which is good news. It means we can still make things smaller, and there's about 1, 2, 3, 4 orders of magnitude before we reach the limit. This is good news and bad news. The good news is we are far from the limits. The bad news is that we are not so far from the limits. You can do even more better calculation by the same paper. You can, if in any approach based on charge transport and change in electromagnetic field, we can define power per energy dissipation and heat removal set the fundamental constant of the system operation. We can define like, this is how much energy per operation we do, how much energy, how much power is being removed. You can define kind of a time constant. So if we look at large collection of devices, when we spend typical microprocessors today, we spend about 100 watt per centimeter square. You got time constant of 5 nanoseconds. While for the individual devices, now 5 nanoseconds is not so fast. 5 nanoseconds is less than gigahertz. It's a 200 megahertz operation, or in the range of few hundred megahertz. Individual devices, you got much better devices. So I think we spent enough time on the limits, and let's go and look and move once. We spent a few minutes on the fundamental physics limits, and the conclusion is that there are fundamental limits based on thermodynamics and quantums functions, but the quantum and the quantum limits and the thermodynamic limits are in the range of 1 to 2 nanometers. Frequency of operation of few gigahertz or few hundreds of gigahertz, depends how we do it. And there is a relation between how many devices we put per unit area and the power. So there are limits. Now, just to illuminate you, we talk about the front end. If you're not familiar with the terms, in VLSI design, when we design a circuit, we have the front end. The front end is a kind of a jargon name for the devices, the transistors. And then if you have the front end, of course, we have the back end. Now it's very confusing because there are two types of back ends, depends which person you're talking